Okay, last time we basically did a fairly rigorous proof of Green's theorem on a small rectangle. Okay. Without annotating everything. But to say the integral of this stuff, path one, what to say minus. Okay, I'm just going to say this differs from the integral over path three. That's what I mean by integral with some parentheses, and I'm not going to annotate any of that. Why? Integral differs because y changed. Okay. If y was the same over this path as this path, since they both go from the same x value, you wouldn't have any change. If this path was right on top of this path, you'd get zero. Okay. Now, when you do this path and then this path in the opposite direction, you're still going to get something pretty close to zero if this function is continuous and your delta y is small. Okay. But since y changes between here and here, those two parts of the path, and that's why those two parts of the path differ. Also, you're integrating in the x direction here, so you're only integrating p on path one and path three. Follows that it's py that causes the change. Okay. And if you integrate py y delta y, it gives you how much change there is. Okay. Now, I'm not going to put all that together. You have a question, where your delta x come from? Well, delta x comes from the fact that you're integrating p with respect to x along these paths. So you're going to get a py delta x delta y. It's going to be negative. And you can see that intuitively if you look at it right, but I'm not going to not going to go that far. But you just write out the py by the definition of the derivative. So that equal to this, which is approximately equal to, well, I mean, that's pretty much it. So that py delta y is approximately equal to px y plus delta y, p of x y plus delta y, which is the value up here. minus P of xy, which is the value down here. Since up here you're integrating in the opposite direction to this, that's where the negative sign comes about here. And if you think it through, you see why it is. But one of the harder things to understand is just people don't really relate well. Usually, I don't know if everybody here does or not. Some probably do, some probably don't. But it's this expression of the derivative, the expression you take the limit of to get the derivative, the difference quotient. And that throws people off because when you start looking at the symbols in that proof, it gets too big, you go blind. Okay, unless you're very good at looking at symbols. So I just wanted to say a little bit more about that and say it comes down to these ideas, and we put them together fairly rigorously on Tuesday. Okay. Okay. Could write our dr as a delta xi plus a delta yj at any given point. This is vector here is tangent to our path. So we're integrating the component of pi plus qj tangent to the path. Delta yi minus delta xj has a negative reciprocal slope to the tangent, therefore it's normal. Okay. On this part of the path, delta y is 0. Negative delta xj is in the downward y direction. You know, j's up this way and i's this way. So this is your normal vector. Similarly, we got a positive delta y on this path, assuming that we're integrating in the counterclockwise direction. So we have a positive delta y here. So we have a delta yi. Well, that's in this direction, right? And up here, we have, again, a delta x. The delta x here is negative, so negative delta xj is in the positive j direction. So you can easily reason out that this thing is always normal. Okay. I'll actually in the habit of having things without thinking about what I'm writing. So the integral of pi plus qj times delta yi minus delta xj are dotted with delta yi minus delta xj. That's the flux through the boundary. Okay. Is the integral of pi plus qj dot n. Okay. And that is, since you've switched your delta y and your delta x, this then turns out to be the double integral over your domain of px plus qy dA. I'm waving my hands a little bit over that, but it comes about because this would be the normal vector, and I don't want to go into too much detail about it. Okay, well, the other thing is, you want to find the area of your region. You just make up a qx and a py such that qx minus py equals 1. Okay, and then you can find the area by doing an integral around the boundary. Now, one shortcoming I think I see in the problems is they say find the integral over this region by doing the line integral around the boundary. Okay, I couldn't find a problem, and I didn't look that hard, but it didn't appear to me that they had a problem. I mean, I looked fairly closely. If they had any problems, it said find the line interval by doing the area. And I'm going to look again. And I'm probably going to sign one of those. Yeah, if I can't find one, I'll just make them up. Pretty easy to make them up, but make up a good one, it takes a little work, so we'll see. Okay, does that make sense? Now, all those things are kind of important for where we're going. All right. And just say that because some people weren't here last time. Then trying to make a little more sense of the proof without getting too ruthless on it. Okay. Um, I want to talk about surface area. First of all, it doesn't matter which use for U and V. In the XY plane, what do we get for a given value of V? Let's just let V, maybe think of V ranging from 0 to 4, but let's just let V equal 3. So what's our shape in the XY plane? Well, this should be pretty obvious if you understand the unit circle definition. It's just a circle of radius 3. But we can prove that. Make sense? So I'm not going to say too much about it. Just that if you do x squared plus y squared and rearrange it, you get b squared times 1. So x squared plus y squared equals b squared. Therefore, b equals the square root of x squared plus y squared. Well, the square root of x squared plus y squared equals b. Then you have a circle of radius b. And if b equals 3, then it's a circle of radius 3. Okay. Well, let's extend this a little bit. Now, I'm not going to leave this on the board. Is that okay if I erase this proof? Because that should be really straightforward in terms of what we've done today in the course. So now I want to add C equals V. And now V goes 0 to 4. So what do we have now? Well, we're now in 3 dimensions. When V equals 0, Z equals 0. So we just have the origin. It's sloppy here, but there it is. Okay. Now, if V equals 4, then we're up here in the plane where V is 4. Just do kind of an auxiliary x, a set of axes parallel to the XY axis. And say that, okay, well, we come out 1, 2, 3, 4 units here, 1, 2, 3, 4 units here, 1, 2, 3, 4 units here, and 1, 2, 3, 4 units here, and we sketch a circle. It'll look something like this. So in the Z equals 4 plane, we have a circle of radius 4. Makes sense? Now, if we look at this, in the Z versus R plane, where R could be the x-axis, could be the y-axis, or it could be any axis through the origin. That means that we're just seeing a point at the origin, and up here in the Z equals 4 plane, -4 and r equals 4. Although if we take r as a radius, it's 4 here and 4 here. It's like on this axis, whatever this axis is, let's not call it r, because that could be confusing. Let's call it a w axis. For w could be any axis that shares the origin down in the xy plane. Okay. In other words, we're cutting this thing at any angle we wish, but with a vertical plane through the origin. Okay. So here w equals -4. Here w equals 4. Okay, so how do we get from here to here? Well, what about z equals 2 plane? Well, in the z equals 2 plane, that means v equals 2. So I'll say in the two, and this describes the circle of radius 2. So we go halfway up to 4, we're at 2. We can do some auxiliary axes here. We come out this far, come out this far, this far, this far, and we get a circle that I'll draw with first with dotted lines. So we kind of see where that circle is, but make it this. Then I'm going to do a straight line from here to here and from here to here. This circle of radius 2 in the z equals 2 plane is going to be tangent to either of these lines. We draw here, we're going to see that z equals 2, w equals -2, maybe w equals 2. And we're going to be looking straight on. We're going to see the edge of a disk of radius 2. And this should convince you that what we're looking at is a cone. And I don't have room to write out all the characteristics, but the cross sections parallel to the XY plane are the circles z equals or x squared plus y squared equals z squared. Okay. And I should write that. Okay, well, we just had a question that anticipates my next exam. Okay, so we'll get to that in a minute. I said it didn't have room to write out everything. Not writing it out as organized as I might like. Cross sections. Those cross sections parallel to the XY planes, circles of radius z for a cross section, or where a plane parallel to the XY plane is a plane where z is constant, right? Okay, I could write the words a little better, but that's the idea. Now, the question that anticipates what I was going to do next time is, don't you automatically have a cone if you have an apex here and a circle of radius 4 here? Well, no. But if you let z equal v squared over 2, you get a paraboloid that has this circle up here. Okay. And you don't really call it an apex, it's kind of a vertex. Now you call it paraboloid. It's sometimes use vertex, whether it's paraboloid or not. So, still, the reason for calling this apex is the cone continues on. You know, I could let V go from -4 to 4, and I'd have a double cone. Okay, and I hope you're familiar with that because you've had to do that with some of the volume integrals and stuff. Okay. So we can so and I said V squared over 2. I really meant quantity V over 2 squared, which would be V squared over 4. Actually, I meant V squared over 2. That was dumb because it's going to be V squared over 4. So that when z equals 4, V squared equals 16, so that V equals 4. Okay. Heavy, something not this morning, but okay. I'll blame it on the hand, but it's got much better say. It's not it. Um, in this case, if we just do these cross sections, it's really easy to see. V versus W. If P equals 4, then sorry, this would be Z equals 4. If Z equals 4, then 4, so V equals magnitude of V equals 4, right? So one way or another, V equals 4 implies then that you're going to have a circle of radius 4 for reasons very similar to this. In other words, X is going to be 4 cosine U, Y equals 4 sine U, etc. Okay. X squared plus Y squared then equals 4. So we've got this. Of course, if V equals 0, we've got Z equals 0, and both X and Y are 0 if V is 0. Okay. Now, if V equals 2, then Z equals 1. get a circle of radius 2. Because if V is 2, we got 2 cosine U, 2 sine U. Okay. And I should put our limits in here. So now it is Z equals 1 plane, our circle is going to have radius 2. Not going to get a straight line from here to here that goes through here. Okay. Now, more formally, section instead of W, and just go to the XZ plane. You can conclude the cross section in this plane is Z equals X squared over 4. Okay. The XY plane, it's Z equals Y squared over 4. Because in the XZ plane, Y is 0, which means that the sine of U is 0, so the cosine of U is 1. So X equals V. So that V squared over 4 is X squared over 4. Understand that argument? That makes sense? Okay. If you're in the X, YZ plane, I put two letters together. My hand just wants to write X, Y, no matter what my brain might be thinking. Oh, total disconnect. Okay. So in the YZ plane, well, if you're in the YZ plane, that means X equals 0, which means the cosine of U is 0, which means that the sine of U is either 1 or negative 1. Okay. In either case, Y is either equal to V or negative V, and V squared and V squared over 4 doesn't care whether it's positive or negative. To get Z equals V squared over 4 again. So we have so our surface of revolution yields a parabola. Parabola in whatever plane through the origin, whatever vertical plane through the origin you want to cut this thing with. I could go to a WZ plane and whatever. Well, I don't want to take the time to work that out. Okay. Now my next question is, what if you want to find the flux of the vector field through this surface, which through this parabola, or through this section of a cone, Frustrum? Okay. You have to have a normal temperature. Put your normal temperature at a given point. Well, you could say here, if for this example, your R vector is V cosine U times I plus V sine U times J plus V squared over 4 times your K vector, right? Agree that okay? Not yourself, because I haven't had you do too much active stuff. What's a partial of R with respect to U? What's a partial of R with respect to E? Okay, so partial of R with respect to U is negative V sine U I plus V cosine U J. Partial of R with respect to B is V times K. Now, what's a partial R with respect to U mean? Well, it means if you change U by a little increment, I'm sorry, you're looking at the point. Let me pause it and let me know what. Told you my brain's not totally with it. I just wrote that down without thinking. But there's the correct partial with respect to B. That's just going to give you cosine U. This is going to give you sine U. It's going to give you 2V over 4, which is V over 2. Okay. Now, what I'm saying though is now, okay, if you change U by a little bit, then vector change is going to be whatever that change of U is times this vector. Okay. Now, what's that change in, or what's the change in this vector? Okay, well, I think I don't want to try to illustrate it with this, because I'm not sure what I was about to say. It's just gonna be all that illuminated. Okay, this is your partial bar with respect to U. This is your partial bar with respect to B. If you take the cross product of these two vectors, I need more room to write it up, so to speak. Room to board accordingly. Okay, so see where the edge of this board is. Okay. Okay, so say this, partial R with respect to U delta U, partial R with respect to V delta V. Factored, okay? V delta U delta V. These are vectors at a specific point. At the point R of UV. And right there is R of UV. Okay. So maybe I should be specific. That is R at UV, but I'm just, generally suppress the UV because we know that's what it is. But, right now we're just seeing it for the first time. So maybe we don't really know what it is until we've had our hands on some of these problems. So I should write it that way. Okay. So these are vectors at the point R of UV. Um, that's the area of the parallelogram form. By the two vectors. Now, what do I mean by the two vectors? I mean this vector and this vector, right? And I use the word incremental in parentheses because we're going to think of, well, let delta U and delta V approach zero. Okay. So these are vectors. They're going to be tangent to the surface. Since they're tangent to the surface, this parallelogram is tangent to the surface. Since two vectors are tangent to the surface, and they won't be parallel unless your surface is two-dimensional. Okay, I won't go that. Okay, they won't be parallel for any of the surfaces we're going to be looking at least, okay? The cross product is all. I mean, if you got two vectors that are tangent to some surface, the cross product is perpendicular to both vectors, so it's got to be normal. Are you convinced of that? You look a little dubious. So Let me know if you're newbies. Okay, again, it's just, if that vector's tangent and, oh man, okay, if that vector's tangent, can't turn the hand that way, and that vector's tangent, okay, no matter whether they're at right angles or not, we don't know what angle they're at. Okay, but they can form a parallelogram, right? And their cross product by the right-hand rule is perpendicular. If they're both tangent to the surface, the cross product has to be normal with the surface. Okay? So parallelogram's tangent to the surface and cross product is normal. Du is partial r with respect to u. Vector t sub v partial of r with respect to the parameter v. And magnitude of tu cross tv times delta u delta v is the area of the parallelogram. Okay, as I said a whole lot of stuff here, and I just wanted to go back and flip through chapter to make sure my notations were consistent, and they're identical, pretty much. It was pointed out to me that if we actually take the derivative of this with respect to v, we get cosine of u, not negative sine of u. So I'm just writing down what I see rather than what I think. If we actually do this, which we're going to do in a minute, good thing if I see this. So now we've come around to the idea that we can call this vector tu, call this vector tv, and those are the two vectors we're going to do the cross product of to get our area infinite. So from here, and we do a little etc. Here up here. I's and j's, not I vectors and j vector subscripts. And we get split area infamous. The ui delta vj. Okay. The sum of the area increments approaches double integral over the region that is the area of the surface. So in this case, du cross 2v equals, and you got three components. It's easiest to do determinant form. And I didn't leave myself room to write the determinant out. Write the components. We have negative v sine u negative plus v cosine u and 0. And then we have v cosine u, v sine u, v squared over 2. And that represents our two vectors. And there's our I, J, K. And we put the absolute value sign around that. And we get, okay? It's just going to be, for I, we're just going to get v cosine u times v squared over 2. Which is v squared over v cubed. Never mind. And j is going to be multiplied by v cosine u. Let's see, I think we have a, on the j, yeah, it's going to be v cubed over 2j. And I'm leaving out my sine and cosine. I'm not clerically competent today. We have v cubed over 2 cosine u times I plus v cubed over 2 sine u times j. And then k, well, k is going to multiply negative v sine u times v sine u. It's going to give you negative v squared sine u, okay? And then it's going to be minus v cosine u, v cosine u, v squared cosine u. And that comes out little v squared k. Something wrong here. Okay, look, this thing is not homogeneous and it needs to be. My TV vector is v over 2, not v squared over 2. These v squared cubes should be v squared. Make sense? And as a result, the magnitude of TU cross TB equals first of all, we can factor out a v squared. Okay. And think of the magnitude, just dot the vector with itself. Okay. Then we're going to get square root of that dot product. And it's v squared times 5/4 if I've done this correctly. Not up to the errors and follow the procedure, but the area is the integral with respect to v and u. V goes from 0 to 4. U goes from 0 to 2 pi. You're just going to integrate 5/4 v squared. That's going to give you 5/12 v cubed over 3. Got details that I've probably done wrong. I just say again, v squared integrates to v cubed over 3. V cubed over 3 evaluated from 0 to 4 gives you v cubed, which is 64 over 3. 5/4 comes out in front, and I didn't bother bringing it out in front. So let me write that down a little more correctly. And since it's 5/4, that's going to be 640 over, well, we've got the 2 factor for 2 pi. So we can deal with that. 640 pi over 6. So 340, that took the 2 into consideration. That's about 150. Does that make any sense? Well, this surface could be inserted inside a cube. Okay. It's 8 by 8 by 4. Well, 8 by 8 by 4 gives you 256. This gives you about 150. Okay. So it makes sense that that fills a little more than half the cube, roughly half the cube. Okay. So it makes a certain amount of sense. It can also be checked because, of course, you can integrate the cross sections. You can integrate pi z squared from 0 to 4. Okay. Get pi z cubed over 4. 64 pi. That comes out a little low. Anyhow, you can check that just by second semester calculus. You can do cross sections parallel with the z-axis. You can do cross sections parallel to any axis and integrate. Okay. Now that result didn't make sense. 0 to 4 pi z squared. And that should give you 64/3 pi. That's something wrong with my brain today. Do you understand the process? To find an area, all you have to do is integrate these area inputs. Now, if you want to find the integral of some function like x squared plus 5y plus pi z over x, okay, whatever. You just throw that function into your integral. Okay. So that to integrate an f of x, y, z, you have something like the integral, more like an integral of f of x, y, z dv du dv or dv du, where f of x, y, z is actually f of u v. Okay. So x is some function we'll call x of u v and so forth, so that f of x, y, z has to be written in terms of u and v, just by substituting whatever our parameterization is. If we have this parameterization, then we substitute v cosine u, v sine u, and v squared over 4. Okay, what if we wanted to do the integral of n with respect to the area? Okay. Well, the normal vector, now that would be a unit normal. The unit normal would be Tu cross Tv over the magnitude of Tu cross Tv. Your area increment is still magnitude of Tu cross Tv. Can I do this? Maybe. Du dv, which just ends up equaling the integral of f dot Tu cross 2v du dv. Okay. And remember that what is the vector Tu cross 2v? It has area, the area increment magnitude of Tu cross 2v times the delta u times the delta v, and it's normal. So you're multiplying, or you're taking the dot product of a function with the normal vector multiplied by the area. And that's your flux. And that's, of course, concept you need to ponder. Get used to. Flux is a big deal. Being really careless today. Normally I'm pretty careless. Today's unusual. I hope it's unusual. I hope it's not this bad every day. Okay, my vector should have been over the T, not over the U, U's not a vector. Okay. That's kind of a summary of what you do now, different surfaces. Well, we're kind of out of time. Read the examples. And email if you have questions, and I know you got, holiday weekend sort of. And you get done what you can. You're a little behind next week. So, better catch up. Like you said, 6-4 wasn't too bad. But you see how those ideas and the ideas that we use to develop the bridge theorem keep applying. Okay, the geometry of everything is big deal. I can't find the right words for what I'm trying to say, but I think you know.